So good morning and welcome to Classical Mechanics 1. Today is the 12th meeting, 2nd of November 2021, Tuesday. I believe the last lecture has ended a bit late, analysis. But now that we are 5 minutes into the class, I think it is time we begin. Are there any questions before I get started? There were a couple of clarifications from last time that I wanted to make before proceeding. Okay, I think, yeah, we have about 42 participants right now. Okay, so last time we were discussing things to do with Galilean relativity, superposition principle for forces, as well as Newton's laws, especially the second and third laws. A couple of things which I wanted to correct or do better this time. So very briefly, I will do that.
Sir.
Yes.
The location of a particle is different from position of particle. Like position changes with the like frames we choose, and like location is independent of frames, whatever we choose.
No, I wouldn't. No, I'm not using location and position in a different sense. I'm using them synonymously. Yeah, the coordinates is a different term, and the coordinates which we use to describe the location do depend on the coordinate system, the frame chosen, coordinate frame. Yeah, the position of a particle is defined in a physical way in relation to other identifiable physical objects like leaves and trees and planets and so on. So the position or location are being used synonymously. They are defined through physical relations with where something else is. Coordinates that you assign are like a address, and they do depend on the coordinate system, the values of the coordinates. Yeah. Or even whether you use Cartesian or polar.
Also, in previous lectures, like in the earlier lectures, you said that location is independent of like whatever. Like my home is still at my location, no matter like which frame I choose. Like it will still be in the like street number this and like that.
Yeah, but I thought we went through this in some detail. What I said is that whether you use one coordinate system on another, and I made the analogy with, I mean, perhaps there is one old numbering system and a new numbering system for houses in a street. Whichever one you use, they both point a postman or a courier to the same house. So in that sense, the location of the house is independent of the choice of coordinates. That is what I meant.
Yes.
Yeah.
Thank you.
Yeah. Right. Yeah. I mean, the location of a home is, I mean, doesn't have a, I mean, it is defined relative to other physical objects. It is said to be 3 meters from Gandhi Maidan, 3 kilometers from Gandhi Maidan in that, and 4 kilometers from something else. Yeah, so the location has to be defined relative to other physical objects. That is our only way of defining a location. And over and above that, we may have a coordinate system as well. Yeah, anyway, it's worth thinking about these things. You do raise a good point. So please continue to think about this and raise it again if it's still not clear. Okay, for now, I want to go back to one small question that had been raised last time or even before that, concerning Newton's second law equation of motion, and in particular, whether we are allowed to add a third derivative term to that equation. And the reason, one reason I gave, which you by which you can eliminate such a term, is by first considering such an equation. So we consider an equation with a third derivative term, which is now a modified version of Newton's second law, mx double dot plus nu x triple dot is equal to some force. Yeah, and now suppose nu is some parameter, some constant, which is non-zero, and f is the force. Let us consider a free particle where the force is absent. Then the equation of motion becomes mx double dot plus nu x triple dot equal to 0. And now we want to see whether this equation respects Newton's first law or not. And Newton's first law says that free particles must move in straight lines with constant speed. So is that guaranteed from solutions of this equation? That's the question. Well, what we did is that we integrated once to get mx dot plus nu x double dot equal to a constant, which I call alpha. Then we can integrate it once more, second time, to get mx plus nu x dot equal to alpha t plus beta. Yeah, I'm just integrating both sides with respect to time. Now beta is the second constant of integration. Yeah, so now we have reached a first order equation. Yeah, this is a first order equation, but we cannot simply integrate it. Yeah, we need to do a little bit of work to integrate this equation, and there are ways to do that. I will just give this equation a name. It's an inhomogeneous equation because x appears on the left but not on the right. Yeah, it's a linear equation because x appears linearly on the left. I mean, there are constants and time-dependent constants on the right. Yeah, so this is an example of an inhomogeneous linear differential equation of first order. Yeah, and you will study these elsewhere. For instance, in a differential equations course, or even in this course at other times. For now, I just want to state the solution of this equation, which I wrote incorrectly last time. So this is the correct solution, a general solution. So the solution is x of t is one part which is linear in time. So that is beta plus alpha t, just the thing that appears on the right-hand side, times some constants like the mass and alpha times nu, divided by m squared. Plus there's one more term, which is a third constant of integration, which I've called gamma, times e to the power of minus mt upon nu. Okay, so I claim that this is the general solution of this third order differential equation with three constants of integration given by alpha, beta, and gamma. Yeah, and you immediately see that this x of t has some exponential time dependence. And if this constant of integration is non-zero and also that coefficient nu is non-zero, this is clearly not the constant speed form, because constant speed means x of t must be some x of 0 plus v of 0 t. That is true about the second term, that is linear in time. Yeah, constant times t plus some other constant. But the first term violates that form. And therefore, in violation of Newton's first law, this free particle trajectory does not have constant speed. Yeah, you can compute x dot. It is not a constant, mainly because of this exponential term. And we conclude that a third derivative term on the left of Newton's second law would not be consistent with Newton's first law. Okay, so this is an argument to eliminate such a term. Last time I had written a wrong solution here, which I am now correcting. Any question about this? I invite you to check this solution. Please take it, differentiate it once, twice, thrice, put it in the equation of motion and check that it actually solves the equation. Yeah.
Can't we derive like Newton's first law from the Newton's second law if we consider that f is equal to m times x double dot? So we are kind of using a cyclic argument in this thing.
No. Okay. No, your question is somewhat different. Newton's first law is like the statement.
First law, we say that if there is no force acting on a particle, it will either remain to be at rest or like continue to move in a straight line with uniform velocity.
Yes.
There is no force. That means m times x double dot is equal to 0. That means acceleration is 0. That means the either it will be like at rest or like there will be some uniform velocity.
Okay. No. So I would like to emphatically say that Newton's first law does not say that in the absence of the force, a particle travels in a straight line. No, this is an oversimplified statement. Newton's first law is a statement of the existence of an inertial frame in which free particles move in straight lines. It is a very, very careful statement about existence of certain frames. Newton's first law tells you that isolated particles do admit such a frame in which their motion is extremely simple. Newton's second law builds on that, saying if you are in an inertial frame and the particle is not isolated, that is, it does feel some forces, then what is its motion? That is, so Newton's first law is not a consequence of the second law. Yeah, though it is easy to mistakenly think, simply put F equal to 0, you get Newton's first law. Newton's first law is a much deeper statement. It is a statement of existence of certain frames of reference. And the second thing you raised, whether this is a, I think you use some kind of word, cyclic argument. I think you meant a circular argument. No, this is not a circular argument. See, Newton's first and second law are postulates of how nature behaves with regard to the motion of particles. And now somebody has proposed a modified version of Newton's second law, and we want to check, is that consistent with the first or not? And we have displayed an inconsistency or a contradiction. So to that extent, I think this is not a circular argument. And is that all right?
Yes, yeah. Yes.
Okay, yeah, but very good. Yeah, it's very important to know what Newton's first law says. It is not obvious at all. Okay, so then I want to go to one more thing from last time, briefly. This is to do with the superposition of forces. Yeah, and yeah, so we did say that we have a superposition principle for forces, namely if a body is acted on by two forces, then you can take the vector sum of the forces and get the resultant force under which the particle will, under whose influence the particle will move. On the other hand, we said also that we do not have a superposition principle for solutions of Newton's equation in general. So that is, suppose you have a solution of the equation of motion for one force F1 and another force F2, but the particle is under the influence of both forces. So you may wonder whether we can somehow generate the trajectory when both forces are present by sort of adding up the trajectories for the individual forces. Now, if you think about this in many ways, you will fairly soon come to contradictory results, and this is definitely not true. I am just going to indicate one counter example here. There are other ways of thinking about it. The idea of adding trajectories is itself rather abhorrent. I mean, it may simply not be. I mean, if the particle is moving on a sphere, then it doesn't make sense to take one trajectory and add it to the other. Then the resulting vector will not even lie on the sphere. So this is almost meaningless in many contexts. But we can still look at it in a context where at least the addition makes sense and ask what happens. So let us take a very simple example, the one-dimensional example of a superposition of two forces. Yeah, one is a linear restoring force. F1 is minus kx. You have a particle moving on a line. It is subject to a linear restoring force which is proportional to its distance from the origin. Yeah, so that is some kind of spring. And also there is a constant force, F2, which is a constant. So no matter where you are, there's a constant force. Maybe if C is positive, it will be pointing towards the right. Now, suppose you have solved the equation of motion for a linear restoring force, and x1 of t is the solution. So x1 double dot mx1 double dot is equal to minus kx1. And you have also solved the equation of motion in the presence of a constant force, suppose. So mx2 double dot is a constant c. Yeah, so these are known trajectories in the presence of these two separate forces. Now somebody says, why don't I consider a new trajectory called x1 of t plus x2 of t? So simply add the two solutions up and let us see what equation this satisfies. Yeah. So let us differentiate in C. So mx double dot would be mx1 double dot plus mx2 double dot. Well, from the previous two equations, yeah, what do we get? Mx double dot, where x is defined as x1 plus x2, would be given by minus kx1 plus c, because I just differentiate x1 and x2 twice. So this is what the total x satisfies. Yeah. However, the desired equation of motion is not that. The desired equation of motion says that the mass times acceleration is the total force, and the total force is given by minus kx plus c, where x is x1 plus x2. Yeah, where the left hand side x has to be the same as the right hand side x. So this is the desired equation of motion, where the total superposition of two forces is present on the right hand side. So if I expand that out, I will get minus k x1 plus x2 plus c. Yeah, so that is the equation we wish to solve. This is the equation we have solved. They are not the same. Okay. So this simple example demonstrates that you cannot get the solution when both forces are present using solutions when individual forces are present. Not in general, at least. There are lots of counterexamples.
Isn't the solution space for second order differential equation, linear differential equation, isn't solution space always a linear space? Doesn't it form linear space always?
Yeah, if you
Newton's.
Yeah, yes, you are right. Newton's equation is not a linear differential equation in general. Yes, and that is another reason why you cannot have such a superposition principle for solutions. That is right. But there is more to the story, because you notice here my counterexample actually involves a linear force and a constant force. Yeah, so even in this case, it doesn't work. But you are absolutely right. One of the main reasons superposition principle doesn't work for solutions of Newton's equation is that the forces are not linear in the position. You're absolutely right about that. Okay, is that okay, Vijay and Rai?
Yes, sir.
Okay, great. Fine. So these were two things left over from last time. Okay, there was one more question towards the end, both beginning and end, I believe, from trying to remember the person's name, Shubham Kumar. Yes, Shubham was asking about Newton's second law. I'm afraid I don't want to go into this in great detail here, but I want to just mention what Newton's second law is. Newton's second law says that in an inertial frame, the equation of motion of a particle, well, in one dimension, is mx double dot is equal to some force. Okay? Sometimes we write this, we define a thing called momentum, linear momentum, as mx dot, and say that the equation of motion can be written as p dot is equal to f. Yeah, so these are equivalent ways of stating the second order equation as a pair of first order equations. All right. I must emphasize in all of this that m is a constant. The mass of a particle is assumed to be a constant. We are not suggesting that m can be a function of time and that this equation is valid. Yeah. So this p dot equal to f, we are not suggesting that that is valid for some non-constant mass, non-constant function of time called mass. That is emphatically not Newton's second law. Yeah, so it will now, and all we have verified is that this equation, this second order equation, when you have a system of particles interacting through interparticle forces, is respecting Galileo's principle of relativity, namely in two frames that differ by a constant a constant speed of constant velocity of relative motion, the equations take exactly the same form. And you cannot tell the frames apart by doing local mechanical experiments. Nothing is stated about a particle whose mass itself is a function of time, in which case if you put m as a function of time and try to differentiate this, you will get an equation which has got first order derivatives of x as well as second order derivative of x. That is certainly not Newton's second law, and we are not proposing that that equation is a law of physics or that it is Galilean invariant. So I would like to emphasize that very emphatically. There are contexts in which one wishes to describe a system whose total mass may be changing in time. Now, such a system is a composite system. It may be a balloon inside which some air is present and that air is coming out, while the balloon is moving around in a room. Well, that is a composite system. You cannot apply this equation uncritically to that. You can apply this equation to each of the molecules in that balloon and so on. And you need to develop an equation for the composite system, including the molecules that are present inside and the ones that are being expelled and whatever thrust is being given to the balloon as a consequence. So that is called the rocket equation and so on, where one does deal with the system with variable mass. But I must emphasize that is not Newton's second law for a particle. This is Newton's second law for a particle, and the mass is not a function of time. So it is not possible to take this equation, assume m is a function of time, and try to show it is Galilean invariant. That is not going to work in any simple way. If you want to develop an equation for a system with variable mass, you need to break it down into its subparts, maybe the rocket, the exhaust, fumes, and so on, and develop some equation. And that is a worthy exercise. And the resulting equation will not be Newton's second law. It will be a effective equation for that composite system. And one can ask—
Excuse me, sir.
Yes.
So, but still it is the derivative of the momentum, right? Even if mass is a function of time.
I mean, I don't understand your question. Sorry, who is speaking?
So it's Debashish.
Okay, Debashish. Could you tell me? Yeah, Debashish Bishwal. Yes, yes.
Sir, we're also, doing the derivative of momentum over a system where the mass is also a function of time, right?
No, I have absolutely said that we are not doing that at all. We are considering a particle, and by definition, the mass of a particle does not change with time. So P is equal to mx dot and P dot equal to F are absolutely equivalent to the original equation mx double dot equal to F. It is merely a convenience to rewrite it in this first order form. We are not suggesting that the mass is a function of time by any means.
Yes, sir, got it.
So is it that if we don't consider it in the Galilean framework, when considering high speed when actual mass is also changing, does the Newton's law itself holds in that case, in that system for a particle?
Okay, so look, we are studying Newtonian mechanics here. One can in later stages study relativistic mechanics, and then Newton's second law has to be modified. Newton's first law continues to hold, appropriately read, but Newton's second law is not anymore valid in this form. One has to rewrite it in a way that is consistent with the laws of special relativity. So yeah, no. So the short answer to the question is that this law doesn't continue to hold. Newton's second law has to be modified in special relativity. That is at very high speeds, approaching those of the speed of light. Yeah. And in that context, the mass of a particle can depend on the speed of the particle, and the situation is different. And one can deal with it. But I emphasize that studying a rocket whose mass is changing with time is the study of a composite system. That composite system can be broken up into a set of smaller systems, each of which satisfies Newton's second law in its pristine form, where mass is not a function of time. You combine those and get some effective equation. Welcome to do that. If you ask the question, a physical question, I am in a ship that's moving at constant speed. Inside the ship, I have a balloon which is expelling some air. Is that system Galilean invariant? Absolutely, it is. If you just do some experiment with a balloon in a ship, that is not going, and you cannot use that to determine whether the ship is moving at a constant speed or not. It is just like watching flies fly inside that room, or throwing projectiles inside that room. Yes. So studying a balloon that is expelling air inside a ship will not help you to determine whether the ship is docked at sea, docked in the port, or moving uniformly in the ocean. It is a different question. What is an appropriate equation of motion for a rocket expelling exhaust fumes? And that is called the rocket equation, which I don't intend to go into right now. It's somewhat of a different question. If time permits, we can study that. But I hope I have made very clear that we are considering particles whose masses do not change with time. That is what Newtonian mechanics is about, by the way.
Yes, so we can continue.
Yeah. Okay, great. Okay, so after these basic or rather comments about questions from last time, discussion from last time, I wish now to proceed to discuss. Yeah, okay, by the way, there was also one more thing about this cubical block of concrete lying on the floor. Yeah, I mean, I think I clarified it last time, but I could do it once again. I was just describing it in the context of Newton's third law. And what we said is that the block of concrete, which is placed on the floor, exerts a certain force on the floor, whose magnitude is given by mg. Yeah, and the floor exerts a reaction force, which is sometimes called a normal reaction. It is equal in magnitude, that is, it is also equal to mg, but points upwards, and it acts on the block. So here we have an illustration of Newton's third law. We have two objects, namely the block and the floor, and they exert equal and opposite forces on each other. It is somewhat of a matter of convention that we call mg the impressed force and n as the expressed force, or mg as the action and n as the reaction. That is all a matter of terminology. You are welcome to call n as the force and mg as the reaction force. That is simply words. They are an action reaction pair. And they act on different bodies. That is important to notice as well. By mg, I do not mean the force of the earth on the block. That is definitely not what I'm talking about here. And if you have not experienced this, try to hold a block on your hand. You will notice that the block is pushing your hand. There is some force there, and to support the block, you have to push the block up. That is all we're talking about here. Okay. Fine. Let me then proceed to, okay, we had a brief discussion of what we mean by dynamics, kinematics, and statics. And I encourage you to read that discussion if you missed it or had a question about it. Otherwise, okay. Okay, so there is a question from Debashish Biswal. Sir, Newton's law in its pristine form assumes that the rate of change of mass is zero. Yes, absolutely. Yes, the mass is masses of particles. Let me be clear. The masses of particles do not change with time. The mass of a particle is the same in two different inertial frames of reference. These are both assumptions that go into Newtonian physics. By assumptions, I mean based on our experience. So yeah.
So in Newton's law, are particles exactly as a point in mathematics, or something different?
Okay, so yeah, I mean, in Newtonian mechanics, when we say a point particle, yes, we mean a point in the sense of mathematics, but we are always aware that we are often trying to describe some physical situation. So a gigantic particle like the sun, for many purposes can be treated as a point particle. A gigantic object like the sun, insofar as its planetary motion is concerned, to excellent approximation, we can take the size of the sun to be 0, because the size of the sun, a few thousand kilometers, is substantially less than the astronomical unit, which is the distance between the sun and the earth. So for those purposes, we can, So when we say it's a point particle, it doesn't mean we cannot use that idea to describe real phenomena. So as long as the size of trajectories and orbits are much larger than the size of the object, we can treat the object as being point-like. And assuming we are not concerned with things like the rotation of the sun, or the other internal structure of the sun and so on. If we want to study those, then the sun is not a point particle. Yes, so Bijayan, is that okay?
Yes, sir. And is there any postulate claiming what point is or mass or something like that?
No, a point particle, it's an idealized concept.
Point particle.
No, I mean, a point particle is an idealized concept. It is a particle whose extent is 0. That's all. But it has a mass. It can have a mass. It can carry energy. It can carry momentum. So I mean, you can think of it as a point on the real line.
Mass
That
change.
Yes, we are supposing that the mass of a particle does not change. Yes. Yes, Bijayan.
Yes, sir.
Okay, I think your audio is very, very weak, in the sense that I find it hard to hear what you are saying. Anyway, is there anything else you wish to ask?
No, sir. Thank you.
Okay, fine. Okay, let me now, just for completeness, though we have talked about this before in various contexts, let me just mention something about dimensional analysis. We have already discussed this here and there, but just to put things in a common language. So physical quantities like the Cartesian components of the position of a particle, or a time interval, or a force, can each be assigned a dimension. And it turns out that in mechanics, the dimensions of all mechanical quantities that we encounter can be expressed in terms of 3 basic dimensions, that of mass, length, and time. So more precisely, what we mean is that any quantity f, any physical quantity f, of which I will give examples now. I mean, this could include a force or a velocity, etc., can be assigned a dimension which is denoted f with a square bracket around it. Yeah, so this is how we will denote the dimension of f, and it would be written as a product of powers of mass, length, and time. And these powers I have called alpha, beta, and gamma. So, of course, for a given physical quantity, one should be able to determine alpha, beta, and gamma using some equation or some definition of the quantity. Yeah. Now there are specific among quantities, physical quantities, those for which alpha, beta, and gamma are all 0 are said to be dimensionless for obvious reasons. There is no dimension. Now, consistency requires that all terms in an equation, such as Newton's equation of motion, must have the same dimensions. So if you have a plus b equal to c, then the dimension of a must equal the dimension of b, which must equal the dimension of c. Okay, so this is a consistency requirement, and this gives a quick way of eliminating some errors in equations. So I encourage you to check dimensions whenever you write equations. This is an excellent way of keeping yourself free of at least some elementary errors. Examples of dimensions of physical quantities. This is hopefully nothing new to you. Mass is denoted m, length is L, time is t, velocity is length per unit time, lt to the -1, acceleration is time derivative of velocity. So it is length t to minus 2. Momentum is mass times velocity, so mlt to the minus 1. And force is mass times acceleration, so you just take the previous line and multiply by m. Energy is force times displacement, at least that's one way to think of it. Yeah, or the work done is force times infinitesimal displacement. So you can multiply this by L and get ml squared t minus 2. Yeah, so in this manner, you can find the dimensions of various quantities. I will give some more examples as we go along. Yeah, I mean, and the study of dimensions is called dimensional analysis. It is surprisingly useful, though it's a simple idea. It is surprisingly useful. Now, just a quick remark on units. The most commonly used systems of units in mechanics are the international system and the centimeter gram second systems. Now, in the international system, or called SI, the basic units of length, mass, and time are the meter, kilogram, and the second. And the unit of force is the Newton. And 1 Newton is 1 kilogram meter per second squared. Sir, what is an example where all the 3 indices are 0? Okay, question asked by Devashish Biswal. Okay, let us consider, okay, I'm giving you the answer. Fine. Let's take an angle theta. Yeah, so theta is an angle. So it may be the angle between a force and a small displacement. Yeah, right. Now, a question is, what is the dimension of an angle? Could you answer that?
So it might be in radians, I mean.
Okay, all right. Let us take that up. Yeah. Okay. I mean, radian is a convenient unit indeed. But to make a long story short, the angle has a dimension 0. So it's L to the power of 0, M to the power of 0.
Oh, so is it predefined? I mean, the dimension of angle is, I mean, sorry, all the indices are 0 in the case of an angle. That's
right. Yeah, I'm giving an example of a physical quantity where alpha, beta, gamma are all 0. So theta, or an angle, is a dimensionless quantity. Yeah. So and I encourage you to think and figure out why this is the case. Let me give you, I mean, there are many ways to come to this conclusion, but you do know that you can compute the sine of an angle. Yeah, and this is something we do all the time. Now, furthermore, we can expand the sine of an angle in a...
So maybe because it is independent of those 3 quantities?
Well, it is not, that is one way to think about it, but I would, I'm not saying it is independent of all lengths, but the point is that an angle may be a quotient of 2 lengths. So, and then the lengths, the dimensions cancel out. And indeed, that is how we define an angle. Yeah. Or if you want to look at it in a different way, we do know that the sine of an angle admits a Taylor expansion, the leading term of which is theta, and then you got additional terms like theta cubed upon 3 and so on. Yeah. And so on. Now, let us impose this consistency condition on this equation. Yeah. Now, the sine of an angle, okay, even before we go to the left-hand side, the right-hand side, for it to be consistent, theta and theta cubed must have the same dimension. Okay. So for consistency, theta and theta cubed must have the same dimension.
Maybe that's why the angle also is axiomatically defined in the case of mathematics.
Yes, the angle is defined as a ratio of lengths. Indeed, yeah. Yes, right. In terms of arc lengths and radii and such things, and therefore it is dimensionless. Yeah, and in this equation as well, the only way in which theta and theta cube can both have the same dimension is for them both to be dimensionless. I mean, if you suppose that the mass appeared somewhere within the dimension of theta, then the cube of the mass would appear here, and that would not be consistent. So indeed, theta has to be dimensionless for this equation to make sense. Yeah, but you're welcome to look at it through trigonometry as well. Look at the infinitesimal angles as the ratio. Yeah, so suppose you have a small angle here. Yeah, let me call it d theta, and this is some r, and then this is some arc length. Yeah, let me call that s. So we say that d theta is r upon is s upon r, right? So the infinitesimal arc length is the infinitesimal angle times the radius. And now moving things to the right, let me expand this. D theta is equal to ds by r, where ds is not this ds, but it is the infinitesimal arc length. So ds and r are both unit length, they're both lengths, and therefore their ratio is dimensionless. Yeah, and therefore an angle must also be dimensionless. So does that address the question asked by Debashish Biswal?
Yes, sir. Yes, sir.
Okay, fine. Yeah, somebody else has asked, Naveen Surya has asked coefficient of friction. Okay, you want to find the dimension of the coefficient of friction? Well, you can do that. Or I don't know, is that the answer to Debashish's question, or this is itself a question? A coefficient of friction is not dimensionless. It has dimensions. I mean, when you say that, I presume you mean that there is a force which depends on the velocity. So this is a simple model for a frictional force.
Sir,
yes.
I think he was telling about coefficient of sliding friction.
Okay. All right. Well, okay. Depending on how we define it, it may be dimensionless.
Yes,
Okay. All right. Then you need to define it, and then we can discuss its dimensions. But anyway, I do want to talk about a very simple model for friction that a particle may experience. So if x dot is the velocity, then the force typically points in a direction opposite to the velocity. So the frictional force can be modeled as some coefficient of friction called gamma times minus x dot, and so gamma could be called the damping coefficient or the friction constant of friction, damping or coefficient of friction. And then you will notice that gamma is not dimensionless. It is the ratio of force divided by velocity. So I encourage you to work that out. So the coefficient of friction is typically not dimensionless, at least defined in this manner. There may be other things you want to define differently. Yeah, perhaps you have in mind a coefficient that looks like a force given by a normal reaction force times some coefficient, and in that case, yeah, okay, if you're thinking of something like F is equal to minus mu n, where n is a normal reaction having the dimensions also of a force, in that case mu is dimensionless.
So, but then all scalars are not all scalars do not have zero dimension, right?
Definitely not. Yeah, yes. Energy is a scalar, it is not dimensionless. Energy is a scalar in Newtonian mechanics in 3 dimensions. It is not a scale, it is not dimensionless. Yeah. Okay, any other question? So somebody, Siddhant Shah, has sent a WhatsApp image. Well, sir, I got this answer for the integration. Well, maybe, okay. Siddhant, do you want to tell me the answer? Because I would need to download this image.
Yes,
and,
sir.
yeah, what
so
is
basically the same, like I was getting the same terms as you got, but then one constant was different.
Oh, you are going back to a different question, namely the motion of a particle with some modified Newton law with a third order.
The mx dot plus vx plus, what is the symbol? The frequency, this one.
New. Mx dot plus mu x double dot is equal to alpha.
Yeah.
Okay.
So here in the second part, you've got an m raised to minus 2, right?
In the second term, yes. In the solution, I have written down. Yes.
I've got an m by mu squared.
Okay. Now, okay, this gives us an opportunity to use dimensional analysis to tell whether I am right or you are right or both are wrong. Yes. So, okay, if you are very keen, we can do that. It is possible.
Sir, 1 second. I think like I'm getting the opposite, like eta, mu and m are interchanged in my answer everywhere. So I think I've used that oppositely, but you're just getting a denominator over here. I'm also getting a numerator.
So, okay, I would first like to request you, please take the equation carefully. You say you have interchanged some things now. I don't know what effect that has. So I would request you to take the equation once again. The equation we're considering is mx double dot plus nu x triple dot equals 0, integrating it twice and then solving the last step. If you still get something that is different from what I've written, please do bring it back and we shall resolve this question.
Okay.
Yeah, but wait, I do want to ask you, the solution that your machine has given you, does it have this exponential term as well as a linear term in time?
Yeah.
Okay, now the rest of them are details about getting the constants right. The very fact that there's an exponential term implies that the solution is not constant speed travel. Yeah, I mean, because constant speed travel must be a linear function of time. And you are basically confirming to me that that is not what you get. Am I understanding you correctly?
Yes, sir.
Okay, great. So please do check the solution, and you can also check it with some machine that you have proposed, and then we will compare our answers. And third parties or the rest of the class are invited to check dimensions in this formula. Have I written the dimensions correctly? Compute the dimension of beta, alpha, mu, t, gamma, and so on, and make sure it actually works out. Okay, and that would be one simple way to eliminate or at least identify errors that.
I think it's correct.
Yeah. Oh, which is correct? Siddhant?
Yeah, yours. Yeah.
Oh, the formula I have written is correct? Okay, yes. Thank you. Now.
Dimension is correct.
Oh, dimension is correct.
About the formula.
Okay, dimensions are correct. Fine, I'm happy to hear that. So Siddhant, I invite you to please check the dimensions in your formula, or first of all, input the right formula in your computer.
Yeah, no, sir, I've like manually integrated it, so.
Okay, fine. Yeah, so go ahead.
Check it out.
Okay, sure. All right, please do check. Yeah, and do come back. We will correct any errors that remain. Okay, any question about this? Back to the past.
A question.
Okay, Romit has a question. Yes.
Is there any background noise for stuff? Because.
Yes, could you speak up, Romit?
Yes, sir. What I was trying to ask for is there any dimension for the ratio between a vector and a scalar having the same mass, length, and type?
Okay, so all right, a good question. Now, to be a bit clear, I will go back to my definition. Yeah, so okay, when we talk about a vector having a dimension, what we really mean is the, I mean, force does have a dimension, but what we mean is that the components of the force, the Cartesian components of the force, also have dimensions, and they are the same as the dimension of force. Now, yeah. So now you are talking about taking the quotient of a vector by a scalar, is it? Oh, sorry, what did you say?
Yes, so something of the sort.
Okay, sure. You are welcome to do that. Newton's law already gives you an example. If the equation of motion says that the force, okay, where have I gone? Dimensional analysis. Yeah, force is equal to mass times acceleration. Then I am free to divide by m, and I will get F upon m is equal to a. And this quantity on the left-hand side can be assigned a dimension, namely the ratio of the dimension of force to that of mass. So
yes,
this does
basically a ratio of a vector and a scalar having the same mass, length, and time dimensions. So the right-hand side would be just a vector with no unit.
Sorry, I didn't understand your latest remarks.
So I mean the ratio of a vector and a scalar having the same mass, length, and time dimensions.
Okay. If you take the quotient of two quantities with the same dimensions, you get a dimensionless quantity. Yes.
So we can have dimensionless vectors too, right?
Oh yes, definitely. We can have dimensionless vectors.
All right.
Definitely. Yeah. Yeah. No problem about that. Yeah. I mean, I will construct one for you. Yeah. I mean, I just take f by mg, okay, where g is 9.8 meters per second squared. Now this quantity is a vector by virtue of having the f up there. It has dimensions of mass to the 0, length to the 0, time to the 0. So this is dimensionless. Now, you may not like that I have defined this, but it is a quantity of the very sort you have mentioned. Is that okay?
All right. Okay.
All right. Yes, Rohit. Fine. So now,
Sir,
yes.
I had a question about the dimensions. So
Yes.
you mentioned that these are typically rational numbers. I'm not sure if I've seen something which is rational but non-integral. Could you give an example of a quantity which has something like that?
Yeah, these things do come up. Yeah. So, I mean, like the power 1/2 would come up quite often. Okay, let me, rather than, let me give you some example of that maybe in the homework.
Okay, sir.
Yeah. So, but yeah, definitely, they do come up. Fractional dimensions do come up.
Okay, sir. Got it, sir.
Yeah,
Thanks.
I'll give you examples, certainly, yes. Okay. Yeah, I mean, it's just that so far we've been looking at rather simple quantities. So, so maybe you have not noticed it so far, but in various models one does encounter. Yeah, let me now go to. All right. So I had just said that in the international system of units. So anyway, your question was an example. I'll just write it down. Example of quantity with a non-integral dimension. Yeah. So one can cook up such things. They are very much around. Okay, so I did mention the international system, abbreviated SI, and there the unit of force is the Newton. Yeah. Now we have also another system of units called centimeter gram second. In this, the corresponding base units are the centimeter, gram, and second, as the name suggests. In this system, the unit of force is called a dyne, and because a centimeter is 1/100th of a meter and a gram is 1,000th of a kilogram, you have a factor of 10 to the power of 5 in relation to the SI system. So 1 Newton is 10 to the power of 5 dynes. Okay, so these are two commonly used systems which you will encounter quite often. Okay. Yeah. Now, let me, any question about these dimensions? Fine. Let me proceed then to give you a few examples of forces and a few remarks about that. Now, the first example I want to mention is gravity. So just a few elementary remarks. The gravitational force played a central role in the development of mechanics. In fact, Newton, I mean, in addition to studying terrestrial phenomena, by terrestrial, I mean earthbound in a lab and such things, or maybe under an apple tree, Newton proposed his universal law of gravitation and developed his laws of mechanics in large part to understand the motion of planets. Okay, so gravity played an essential, I mean, a very important role in the development of mechanics. And Newton proposed a law of gravity based on Kepler's laws and other observations of planetary motion. And Newton's law of gravity says that the force between 2 point masses Yeah, so it's a statement about point masses. M1 and M2 is attractive, first of all, and proportional to the product of the masses. And inversely proportional to the square of the distance of separation. Yeah, so I'll write a formula in a moment. So let's first draw a picture. Here is our system. Two masses, M1 and M2. At a certain instant of time, they are located at these 2 points. We set up a coordinate system or a frame of reference with an origin O over here, and M1 and M2 are located at the position vectors R1 and R2. Okay, so now the force due to M1, the gravitational force due to M1 on M2 is attractive and therefore points this way. So I call that F1 on 2. And similarly, the force of M2 on M1 must again be attractive and points this way. Now, we have made a statement about the magnitude of this force, this gravitational force, as well as the direction. So now we are in a position to write a formula for the force. So first of all, just notice from the figure that if R1 is this vector and R2 is that vector, then the difference R2 minus R1 points from the first mass to the second mass. Okay, so the mnemonic is that it points towards the vector with the positive sign and from the vector with the negative sign. So R2 minus R1 points from M1 to M2. Okay, that is simply from this triangle law, parallelogram of addition subtraction, which you did in the first homework set. I have translated the vector R2 minus R1 to emanate from M1 rather than from the origin. So I simply translated that vector R2 minus R1 to that origin. Yeah, so we will use that vector to write down Newton's law of gravitation. Okay, so first of all, we said it is proportional to the product of masses and inversely proportional to the square of the distance of separation. Now the constant of proportionality is called Newton's gravitational constant, denoted G. So with this setup, we can write a formula for the force. The force of the first mass on the second, F1 on 2. F1 on 2 must point towards which force, which mass? The first mass acting on the second mass must point towards?
The first mass.
Yeah, must point towards M1. Yeah, and therefore it must be proportional to R1 minus R2. Okay, so because it must point towards M1, emanate from M2. Okay, so we infer that it must have this, and that is indeed seen in this formula because you have a minus sign and R2 minus R1, so it becomes R1 minus R2. Now it only remains to get the magnitude correctly. We said that it must be proportional to the product of masses, so we put M1 and M2 in the numerator, and it's inversely proportional to the square of the distance of separation. So we put R1 minus R2 magnitude cubed in the denominator because there is already an R1 minus R2 in the numerator. So that in effect, we are dividing by the square of the distance. Now there's a proportionality constant, which is G. Okay, so this is a small exercise on taking the statement in words and writing an equation. So did you follow how we did that? Because we do a lot of fancy things quickly. I want to make sure this simple thing is understood. Okay. Fine. Let us then go to by Newton's third law, M2 exerts an equal and opposite force on M1, and so we can write F2 on 1 as simply minus F1 on 2. Okay, so we can simply reverse the sign to get a formula. Okay, so this takes care of the force between point masses, but often we are interested in a force between a composite system like a star and a satellite and things of that sort. So how do we deal with such situations? Well, Newton's law of gravitation applies to point particles. However, it may be used to calculate the force due to extended bodies, such as stars and planets, on point masses to begin with, or one extended body on another extended body. Okay, between that is also of interest. Now, in order to do this, one repeatedly uses the principle of superposition of forces, linear superposition of forces, which we discussed earlier. And that statement will come in handy here. It states that the force due to two objects on a given particle is the vector sum of the individual forces. So, so we repeatedly use this to find the force that a composite body may exert on a single particle. Yeah. And sort of in the opposite direction, the force on a composite body is the vector sum of the forces on all its constituents. Okay, so you need both of these sort of superposition principles. So let me just at least say qualitatively indicate how you would use this in one or two examples. For example, it is possible to show using the principle of superposition that the force on a point mass m that lies outside a spherically symmetric mass distribution, yeah, like a star, idealized star, is the same as the force due to a point particle with mass equal to that of the total mass of the star located at the center of the star. Okay, so that's a mouthful, but what we're saying is that suppose you have a spherically symmetric mass distribution here, like a star, total mass m, and you have a particle here of mass small m, then the Newtonian gravitational attraction that small m feels due to the presence of this one, it points this way and has a magnitude exactly given by gmm upon separation squared, r squared. Yeah, and it points upwards. I've indicated that here. This may not be obvious, but one needs to establish it. Basically, in principle, one needs to account for all the elementary masses within capital M, find out what kind of force they exert, add them all up, and get this. This is not a surprise because you can use symmetry, right? If you have an elementary mass here, there is an equally, a diametrically oppositely located elementary mass on the other side, both of which will exert forces of the same magnitude, slightly different directions, but the two directions are equally at equal angles with respect to this vertical, and therefore their sum will point along this vertical. So you repeatedly use such symmetry arguments to argue that the force due to this big mass, spherically symmetric mass distribution M, must actually point towards its center. Okay, so I'm not doing the details here because what I've explained is the story, but if one wants to do it in detail, one needs to integrate and so on. This sort of thing is something one does in electrostatics, electromagnetism courses. So I will leave that for discussion over there. Yeah. For reasons that will be mentioned in a moment. You might wonder what is electromagnetism to do with gravity. So I have not said that yet. Okay, let me give you another example. Suppose, for example, the force due to a thin spherical shell of radius r and mass m centered at the origin. Okay, so suppose we have a thin spherical shell, this one, thin spherical shell centered at the origin of mass m. Yeah. Now we have a point mass small m, yeah, located at a location capital R, boldface r. Suppose it is outside the shell, then by the previous argument, the force that it will feel is as though the shell is taken as a point mass located at its center. Yeah, so that is what we discussed previously. On the other hand, suppose the mass was located inside the shell. You might ask, what force does the particle inside the shell feel? The answer is that it turns out that the force vanishes inside the shell. And one can see why that is the case through some clever symmetry argument. Basically, forces due to different parts of the shell cancel each other out. I can explain that qualitatively here. Yeah, so this, let me remind you again, we have a thin spherical shell with total mass m. Yeah, so it's a composite body. We want to know what force it exerts on this small mass m over here. Now we will consider little elementary parts of this shell, yeah, located at the bases of these cones, which I erect with apex at the particle considered. Yeah, so m is not at the center, m is just somewhere. Yeah, I draw this little cone with a small angle. It will cover a small patch on the sphere here, and even smaller patch here. Now I claim that the force due to this patch and that patch on the mass m are equal and opposite in direction and cancel each other out. Why is that? Well, suppose this distance is r1, then and this distance is r2. Then the area of this patch is proportional to r1 squared, whereas the area of this one is proportional to r2 squared. Why is that? I mean, I'm assuming that this angle is small. The area is proportional to the square of the distance, because the angle subtended, we already argued, is proportional to the distance. Yeah, because that is the definition of angle. Angle is basically arc length divided by radius. Now the area is basically proportional to the square of the arc length. Yeah, so that's why I'm getting this. So the areas of these two patches grow with the square of the distances. And therefore the mass in this patch and that patch will also grow with the square of the distances, because it's uniformly distributed. The mass in this patch is proportional to the square of the, is proportional to the area, and therefore the masses are each proportional to the distance squares. So that's the mass present here and mass present here. Now the force due to this mass is equal to this mass. So you'll have something like r1 squared times some constant times m divided by r1 squared. That's what Newton's law of gravity tells us. G m1 m2 upon r squared. Now this one is the mass of the patch. We just argued that the mass of the patch is proportional to the square of the distance. But Newton's law also tells that you have to divide by r1 squared, because that is the square of the distance of the patch from the point considered. We notice that the r1s cancel out. Therefore, the force due to this patch and that patch are equal, and they point in opposite directions. This one is in this direction, that one is in that direction. The two arrows are actually equal in magnitude, equal in length. So for that reason, diametrically opposite patches cancel out insofar as their forces on m are concerned, and we conclude that the total force on this test mass m is 0. Okay, so this, I have sketched the argument. I encourage you to think about it if you didn't catch it. But any question about how we went about this?
So could you once tell again how area is proportional to R2 square? I didn't get that part.
Okay, sure. So this is a question from Saptarshi Sadhukan. Yes. Okay, look. Oops, what is happening? Yeah, so see, I've got a small angle and a little roughly circular. This is a cone. Here is a cone. I'm positioning a cone with apex at the point M, where M is located, and that cone would go and cut the sphere on a roughly circular patch, a disc, circular disc, roughly circular disc. Yeah, I mean, it bulges out a little bit, but for small angles, it is roughly a circular disc. We ask, what is the mass of that disc? Now, let us suppose that mu is the mass density. Mass density of that shell. That is some fixed number. Then the mass of the disk is equal to mu times the area of the disk. Is that okay, Saptarshi? So
Yes,
far?
sir. Yes.
Okay. Now all we want to know is what is that area. Now that area is basically pi r squared. Yeah. Yeah. So where r is the radius of that disk.
Yes.
Yeah. And now I am estimating that using this little trigonometry. Is that where your question lies?
Yes, technically. I mean, I thought, yeah, I was thinking about
okay.
Like you said.
Sure. So, okay, let me just finish the argument here. So let us suppose that this distance is R1. Yeah, I mean, you can do this for R1 and R2. It's all the same. So the according to our basic definition,
okay, so tan theta equal to theta, that, yeah.
Exactly, yeah. For small angles, tangent of theta is approximately theta. So if I call this theta, then the tangent of theta, is equal to this this radius of this disk, which I will call, let me call the radius rho divided by R1. And therefore rho is equal to R1 tan theta. And that is it. So then the area of that disk is going to be the square of rho times pi. Yeah. And so it's going to go like the square of R1 times pi times the square of tangent theta. Now theta is the same in both directions. I mean, these are a pair of straight lines intersecting, so the angle here and there are the same. So does that tell you why the area is proportional to R1 squared tan squared theta times pi? Is that formula acceptable?
Yes, yes.
Okay, so is your question answered?
Yes, more or less. I'll think about it more.
Oh, okay. Okay, fine. If there is anything I can clarify now, please do tell me. The message is that the area of this disk is proportional to the mass of that disk, or more precisely, the mass of the disk is proportional to the area of the disk, because there is a constant mass density mu. So we just need to compute this area, and it is all in the small angle approximation. So this disk is actually not in a plane; it is bulging out a little bit, but those are small corrections which in the limit of small angles go to 0, and therefore we can approximate the area of that disk by pi rho squared, and then we compute rho using basic trigonometry, and find that radius of that disk is proportional to the distance of the disk from the point mass m. So then it goes like R1 squared. There is nothing more to it. But yes.
Just a question. In here, since the law is inverse squared law, so it is happening, right? For uniform mass distribution. So suppose we have a force which follows inverse cube law. Can we say that if the radial symmetric mass distribution is proportional to the radial distance, that is, the mass distribution is no longer uniform, will this same shell theorem hold?
No, if the mass distribution is not uniform, there will be asymmetries. Then this will not hold.
We are again considering cube law, and we are making the mass distribution grow linear with radial distance, like something like that, actually. Or maybe some 1 by r power n distribution, and somewhat we are making r power n minus 2. We are growing the mass distribution. Will that follow again the block?
Okay, so I think
theorem kind of thing.
Okay, see, I think I have not. You have not been able to express your distribution very clearly. From what I can make out, you are trying to get some cancellation to happen. I think you are saying that the mass distribution is not uniform, then you have to say what is the distribution.
Yeah, the distribution, the mu mass distribution is radially symmetric, and from the radially symmetric, that is radially it is constant, and at a radial distance r, it is like some constant into r.
Okay.
So,
Okay. So you are basically trying to get the same kind of cancellation by changing the force law and also changing the mass distribution. Okay, sure. Yeah, I think that would work. Yeah, if you change mu into a mu as a function of angle, is that what you're saying?
Radial distance.
Mu is a function of radial distance. But wait a minute, this was a spherical shell. So
Yeah.
I'm not understanding what's happening. You are then r is the same for all. What are you saying?
No, radial distance, I mean, mu r is the a point within the shell at a distance r, and consider a sphere of mass that is with the mass in the elementary angle with dx distance, it is some r into dx, r into dr, precisely.
Okay, so I get the spirit of what you're trying to do, but I think you need to think about it a little bit more clearly so that we can fruitfully talk about it. You have to clearly say what is the mass in a disk. I mean, it cannot depend on where I position the test mass. Okay, I'm perhaps I'm misunderstanding you, but you are giving me some scheme to adjust the mass in this disk so that the 1/r³ law will get cancelled out. You are welcome to do that. I am sure this will work if you are careful about it. Yeah. So I mean, I get the spirit of what you're trying to do. I think something like that will work out.
Okay. Thank you.
Yeah. Any question? But by the way, people did consider 1/r³ force laws well after the time of Newton in order to explain certain discrepancies in the motion of the moon, calculated versus observed. And eventually, all those discrepancies went away when the calculations were done even more carefully. It took a long time. Yeah, so people have considered 1/r³ laws. And but all evidence now points to a 1/r² force law. At least it is able to explain all the observations. But there was a time when Newton's law was doubted, and in fact, Newton's own calculation of the motion of the moon turned out to give the wrong precession of the lunar perigee. And that was something that Newton was not able to resolve, and it took nearly 100 years for that to be resolved, I think, in the work of Clairaut later on. The same Clairaut whose theorem on equality of mixed partials we talked about earlier. Yeah. So, such laws have been considered, and they can arise in other contexts also.
Okay, sir. Thank you.
Yeah. Okay, now a couple of, I am out of time. I just noticed that it is 1:13 p.m. and that is also the time shown in my screen. So perhaps I need to stop here, and we shall proceed next time, continue next time. Next on Thursday, day after tomorrow, we have a holiday due to Deepavali. So I wish you all the best. Please stay safe, but we will not have a class. Our next class will be next Tuesday. The assignment number 5 is due this Friday. So please do submit it on time, well in time, and ensure that you submit and not just leave it as a draft. Okay, any questions before we close?
Sir, not a question. I just got
Yes.
my mistake. Your the integration was like correct. I got my mistake.
Okay, so Siddhant Shah is confirming the integration that we proposed for the third derivative third derivative of position modified Newton law. Okay, so you are confirming this formula number 54. Is that correct?
Yes, sir. Like by manual integration and by dimensional analysis.
Okay, you check the dimensions. Fine. Okay, I'm very glad to hear that. Okay, so that gives a nice application of dimensional analysis. I encourage also other students to work out the dimensions of all the terms here and alpha, beta, gamma, delta, etc., and check that it is dimensionally consistent. That is a nice exercise. Okay, any other question? All right. If not, we will stop this meeting and all the best. And we will meet next week. Thank you. Yeah.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you.